Hi friends, welcome to the lecture of Advanced Discrete Mathematics. Today we are going to study a new concept which is a pigeonhole principle, which is very useful in the most of the examination. Okay, that is the pigeonhole principle can be used. We can use in most of the competitive exams. Okay, pigeonhole principle. Okay, now we have to see what is a pigeonhole principle. Okay, a pigeonhole pigeonhole principle is also known as a Dirichlet drawer principle or showbox principle, and a pigeonhole principle and is useful in counting methods. Okay, there are so many problems which can be solved by using these methods. Counting methods. Okay, now we have to see what is the actual statement of the pigeonhole principle. Okay, let us see what is the statement. That is statement. If young pigeons are assigned to young pigeonholes, then there must be at least two pigeonholes. At least two. Then there must be at least two pigeons. Sorry, if young pigeons are assigned to young pigeonholes, then there must be at least two pigeonholes. Sorry, pigeonholes that contains pigeonholes. Then there must be at least one pigeonhole that contains two or more pigeons. And for that, this m must be less than, that is the number of pigeonholes are less than the number of pigeons. What will be the statements? If young pigeons are assigned to young pigeonholes, then there must be at least one pigeonhole that contains two or more pigeons. And for that, this condition is required. That is, m must be less than n. As m is less than n, then the m is nothing but the number of pigeonholes, and n is nothing but the number of pigeons. As the number of pigeonholes are less than the number of pigeons, then there must be at least one pigeonhole that contains two or more pigeons. Okay. Now let us prove this one. The young pigeonholes be numbered with the numbers 1 to m. Okay, give the numbering of m pigeonholes starting from 1 and End of this is nothing but m. That is, the m pigeonholes can be numbered from 1 to m. Okay, and beginning with pigeon 1, beginning with pigeon 1, each pigeon is assigned in order to the pigeonholes with the same number. Okay, that is, first we have to give the numbering of pigeonholes. After that, each pigeon also give a numbering from 1 to n, and corresponding pigeons are put into this m pigeonholes. As but here, since m is less than n, that is, number of pigeonholes is less than the number of pigeons, the number of pigeons, so n minus m pigeons are left without having assigned a pigeonhole. Since we have put each pigeonhole contains one pigeon, then there are n minus m pigeons that are left without having assigned a pigeonhole. Okay, therefore from this we conclude that the remaining n minus m pigeons, now we have to put in these m pigeonholes only. Okay, as we put these n minus m pigeons in pigeonholes, then from this we conclude that there must be, thus there is at least one pigeonhole which contains two or more pigeons, and hence the required value. Since we have put first we have giving the numbering for m pigeonholes, and then we have put this n among from these n pigeons we have put m pigeons in these m pigeonholes. Then there are n minus m pigeons are left without having assigned a pigeonhole. Now we have to put this n minus m pigeonhole in one of these pigeonhole, or we can put some of them in first pigeonhole, some are in second pigeonholes, and continuing in this way. Therefore, from this we conclude that there is, if we suppose this n minus m pigeons are put in only one pigeonhole, then from this we conclude that there is at least one pigeonhole that contains two or more pigeons. Okay, and hence the, let us see the examples depending on this principle. Okay. Example. First one, in a group of 13 children, there must be at least two who were born in the same month. Same month. So here we have given that there are 13 children. Now we have to prove that out of these 13 children, there must be at least 2 children who were born in the same month. Now we have to use the pigeonhole principle for this example. Okay. Now here given that there are 13 children. Let us consider these 13 children as the pigeons. Let us consider the 13 children as a the 13 children as a pigeons, and the 12 months of the year as a pigeonholes, okay. So there are total 13 children and 12 pigeonholes. That is, according to pigeonhole principle, there are 13 pigeons and 12 pigeonholes. As 12 is less than 13. That is, 12 is nothing but the number of pigeonholes and 13 is nothing but the number of pigeons, which is from the according to pigeonhole principle. Okay, as 12 is less than 13, that is the number of pigeonholes are less than the number of pigeons. From this we conclude that there must be out of these 13 children, there must be at least 2 who were born in the same month. Since if suppose out of these 13 children, we take 12 children are born in one month. That is 12 children from these 12 months. That is, first one is from January, second one is from February, and continuingly 12th one is in December. Now there is left one children. Now we have to take this one children among these, that is, this one children is born in one of these 12 months. Therefore here there is a possibility that there must be at least 1 month in which there are 2 children born. Okay, so from this we conclude that out of these 13 children, 2 are born in same month. Okay, now next example is show that if any 5 integers from 1 to 8 are chosen, then at least then at least two of them will have a sum equal to 9. Now here we have to show that if any 5 integers from the positive integers 1 to 8 are chosen, that is from 1 to 8 we have to choose any 5 integers, and then we have to prove that at least 2 of them will have a sum equal to 9. Okay, let A be a set which contains these 8 numbers 1, 2, so on. 1, 2, 3, 4, 5, 6, 7, and 8. Now the different sets. Now we have to find out the different sets. The different set each contains two numbers from A whose sum equal to 9 are. Now we have to find out the different sets which each set contains two numbers from this set A. Now we have to find out such sets. Let A1 be a set which contains 1. As we have taken 1, now each set we have to take only 2 elements, and that 2 elements will have a sum 9. If we take 1, then corresponding element is nothing but 8. Okay, A2 which is equal to 2 7, A3 which is equal to 3 comma 6, and A4 is equal to 4 comma 5. These are the only possible sets. If we take next one is 5 comma 4, which is nothing but A4. Next one is 6 3, which is nothing but again A3. So these are the only 4 different sets. Each contains 2 numbers from the set A whose sum is equal to 9. Now let us consider these 4 sets as a pigeonhole. Let these 4 sets are pigeonhole, and the 5 numbers which are chosen from 1 to 8 are considered as pigeons, and the 5 numbers are pigeons. Okay, then again by pigeonhole principle, the number of pigeonholes are less than the number of pigeons, since 4 is less than 5. Therefore, according to pigeonhole principle, there must be at least one pigeonhole that contains 2 or more pigeons. So, if we take any 5 integers from 1 to 8, then there must be at least 2 elements who belonging to one of these sets. Okay, that is, if suppose we have choose first 4 numbers from 8, these 8 integers, that is 1 to 4. For example, if we choose first 4 numbers. Now, if from these 8 integers we have to choose 5 1, therefore there is one left over. If we take any number from remaining numbers, that is from 5 6 8 5 6 7 and 8. If we choose 5, then the 5 integers are nothing but 1 2 3 4 5, and this 5 plus 4 is nothing but 9. Therefore there must be at least 2 whose sum is 9. If we take 6, then 3 plus 6 is 9. If we take 7, then the 7 plus 2 is 9, and if we take 8, then it is 8 plus 1 9. Similarly, if we can take any 5 elements from these 8 integers, then at least 2 of them is belonging to one of these sets. Therefore this is the required. Therefore the P1 condition holds. That is, if we choose any 5 integers from these 8 integers, then there must be at least 2 integers which have a sum is equal to 9. Okay. Now, from this we conclude that the pigeonhole principle, there is one important note. The pigeonhole principle tells us nothing about how to locate the pigeonhole that contains two or more pigeons. Okay, from pigeonhole principle we conclude that the pigeonhole principle tells us nothing about how to locate the pigeonhole that contains 2 or more pigeons. That is, it does not tell us about the location of that pigeonhole, but it asserts only the existence of such pigeonhole. Asserts only the existence of pigeonhole that contains 2 or more pigeons. Okay, and from previous 2 examples we conclude that to apply the pigeonhole principle, apply the principle, one has to decide which object will play a role of pigeon and which object will play a role of pigeonholes. Okay, that one is the important in pigeonhole principle. That is, we have to choose from these two, from given objects, which object will play a role of pigeon and which one is the play a role of pigeonholes. If we choose the correct one, then we can easily solve the given problems. Okay. Now the next one is generalize the pigeonhole principle. Generalize the pigeonhole principle. Okay. Now we have to see the another statement of a pigeonhole principle. If n pigeonholes are occupied by kn plus 1 or more pigeons where k is a positive integer, then there is at least one pigeonhole. There must be at least then there must be at least one pigeonhole that contains k plus 1 or more pigeons. Okay. So here we have to do that. Or we can say that if n pigeonholes are occupied by kn plus 1 or more pigeons where k is a positive integer, then there must be at least one pigeonhole that contains k plus 1 or more pigeons. Or we can also say that there must be at least one pigeonhole which is occupied by k plus 1 or more pigeons. Okay, both are same. Let us see one example depending on this principle. Okay, a bag contains black, blue, and white socks. Find the minimum number of socks needs in order to get two pairs of 1 minute. Minimum numbers of that one needs to choose in order to get two pairs of socks. Minimum number of socks that one needs to choose in order to get two pairs of socks pairs of socks of the same color. Of the same color. Okay. So here there is one bag which contains three colors of socks, that is black, blue, and white. Now here we have to find out the minimum number of socks that one needs to choose in order to get two pair of socks. Two pair of socks means there are four socks of the same color, that is four socks of the same color. So according to this pigeonhole principle, these socks, black, blue, and white, can be considered as a pigeonhole, and pigeonhole is nothing but n. So here, n is nothing but 3. That is, these three colors can be considered as a pigeonholes. And here also, here also given that here we have to find out the four socks of the same color, that is k plus 1 is also given, and here also k plus 1 is equal to 3. Sorry, k plus 1 is equal to 4, which implies k is nothing but 3. That is, here we have to find out the minimum number of socks that one needs to choose in order to get two pairs of socks. Two pairs of socks means there are four socks of the same color. That is here we have to given that k plus 1 is nothing but 4. As k plus 1 equal to 4, then k must be equal to 3. Therefore, now we have to find out the next nk plus 1, this one. So kn plus 1 is equal to, k is 3 and n is also 3. So 3 into 3 plus 1, which is equal to 3 into 3, 9. 9 plus 1, 10. So here there are minimum 10 socks are required so that two pairs of socks of the same color. So the minimum number of socks will be required is nothing but 10 socks are required. Okay. Now, next pigeonhole principle is extended pigeonhole principle. Extended pigeonhole principle. Okay. If young pigeons are assigned to young pigeonholes, and young is greater than young, there must be at least there must be at least one pigeonhole contains n minus 1 upon m plus 1 pigeons, where the symbol is nothing but is the greatest integer value, less than or equal to yes, or equal to yes. That is the symbol. It is nothing but the greatest integer function, and greatest integer function of x is nothing but the greatest integer less than or equal to x. So, if suppose there are young pigeons which are assigned to young pigeonholes, and these young pigeons, number of pigeons are greater than the number of pigeonholes, then there must be at least one pigeonhole that contains at least that is, if n pigeonholes are assigned to n pigeonholes and n is greater than 1, then there is one pigeonhole, one pigeonhole contains at least greatest integer function of n minus 1 upon m plus 1 pigeon. Let us see the example depending on this one. Okay. If 9 books are kept in 4 square, then there is at least one shape that contains at least three books. Okay. If there are 9 books which are kept in 4 shelves, then there is at least one shelf that contains at least 3 books. Okay. According to this pigeonhole principle, the 9 books are considered as number of books are greater than the number of shelves. Therefore, this 9 can be considered as the number of pigeons, and 4 are nothing but the number of pigeonholes. And therefore, m is nothing but 9, and m is equal to 4. Now we have to prove that there is at least one shape that contains at least 3 books. Then according to this pigeonhole principle, that contains greatest integer function of n minus 1 upon m plus 1, which is nothing but greatest integer function of 9, n is nothing but 9. 9 minus 1, 8. 8 divided by 4 plus 1, and which is nothing but 8 divided by 4, 2. And greatest integer value of 2 is 2 only. Okay, which is equal to 3. Therefore, from this we conclude that there is at least one shelf that contains at least 3 books, and hence the required result. Okay. Now, the next principle is pigeonhole principle of second form. Pigeonhole principle second form. Okay. Now let us see the statement. Let f be a function from a finite set yes to a finite set y, and cardinality of x is greater than the cardinality of y. That is, the set x contains the more elements than the set y. Then f of x1 is equal to f of x2 for some x1 comma x2 belonging to x, and x1 is not equal to x2. That is, there must be at least two elements in the domain have a same image in codomain. Okay. Given that f be a function from, that is here given that f be a function from a finite set x to a finite set y, and cardinality of this x is greater than the cardinality of y. That is, there is at least one element is more than the set y. Okay, and if we define a function from the set x to this function, this set x to set y, then as cardinality of x is greater than the cardinality of y, then there is at least one element in the x which have the same image in, at least two elements in the x which have a same image in y. Okay, since if suppose there are 4 elements in x and there is at least there are only 3 elements in codomain. Now, if we take each element have a distinct image, then the first one is going to A, 2 is mapped on B, 3 is mapped on C. Now, as given that f is a function and any mapping is said to be a function, if each element in domain have a unique image in codomain. As given that f is a function, then any element of its domain must have a image. Therefore, the element 4 also have a The element 4 also have a image. Therefore, this 4 is mapped on one of these ABC. One of these ABC, then there are at least two elements in X which have same image in Y, and that is the given principle. Okay, let us see one example depending on this principle. Show that in any set of 11 integers, there are two integers among these 11. There are two whose difference is divisible by 10. Okay. Now we have to use the previous pigeonhole principle for this example. Okay. Now let the set A of pigeons is nothing but pigeons is the set of 11 integers. 11 integers. That is the set A contains the integers from 1, 2, 3 up to so on 11. Which is we have taken this A as a particular these elements 1 to 11. That is here we can take any 11 integers in the set A and which can be considered as a pigeons. And the set of pigeonhole is the set B which contains 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. That is the remainder when which is divisible by 9. Okay, any number which is divisible by 9, then its remainder is one of these 10 numbers. Okay. Now here we have to define a mapping from a set A to set B, where cardinality of set A is 11 and cardinality of set B is 10. That is, it contains 10 elements and it contains 11 elements. Then by previous pigeonhole principle says that if there is a function from a finite set A to a finite set B and cardinality of A is greater than the cardinality of B, then there are at least two elements in A which have a same image in B. Therefore, if we take any 11 integers, then there are at least two numbers whose difference is divisible by 3, which is from the previous principle. Let us take this A as A is nothing but integers from 1 to 11. Okay. And B is nothing but the numbers from 0 to 9. Therefore, here, according to previous principle, here we have to find out at least two numbers whose difference is divisible by 9. Or there are two numbers whose difference is divisible by 9. So here, numbers 1 and 11 are two numbers whose difference is divisible by 10. That is 1 minus 11 is nothing but minus 10, or 11 minus 1 is nothing but 10, and which is divisible by 10. And hence this statement is true. Okay. Thank you for watching the lecture.